This is the screencast for section 2.6, example 1. Rational functions. You have seen rational functions over and over and over again so far, but now we're going to really pick them apart and define what they're all about. So first let's talk about the domain of a rational function as well as its behaviors, and specifically end behaviors. Find the domain of f and use limits to describe its behavior at values of x not in its domain. So first of all, the domain of this function, without even plugging it in, I can tell is negative infinity to 2 and then 2 to infinity. Now I know that because 2 will make the denominator 0, you can't divide by 0. I also know that this is the basic function 1 over x that has a horizontal shift right 2. So I already know what the graph is going to look like, but just in case, I graphed it. So let's describe what's happening with our limits. Now specifically, this problem tells us to use limits to describe its end behavior at values of x not in its domain. So values of x not in its domain, in this case, is x equals 2. There are two end behaviors where x equals 2. There's this top one and there's the bottom one. Now, each end behavior will be expressed as a limit. The limit of f of x as x approaches some number will equal something else. So you are describing the end behaviors in two different ways, just like you did in section 2.3. This time, the limit of f of x as x approaches 2, the y values, now wait a second, as x approaches 2, there's two different pieces. So we have to clarify between the two different pieces. Let's talk about this one first. We call this from the right. So I'll put a little plus sign, and that means from the right. So the limit of the y values, or f of x, as x approaches 2 from the right, is positive infinity. They will keep going forever. So if I plug in x values closer and closer and closer to 2, those y values are going to get higher and higher and higher. Now this one down here is the limit as x approaches 2, this time from the left, of f of x equals, so as I approach positive 2 from the left, so coming in from the left, my y values are going down to negative infinity. So the x arrow talks about what's happening left and right for the function, which makes sense because the x-axis goes left and right. And then the f of x part tells us whether the function goes up or down, and then to what value. Now, just in case you want a refresher, this end behavior out here, which the problem did not ask us for, I'm just, going above and beyond because I'm a teacher and that's what I do. The limit of f of x as x approaches, so as we go all the way out to the right here, that's positive infinity all the way out to the right. The y values, the f of x values, are going to approach 0. So we're going to get no lower than 0. Then on the left here, the limit, like I said, left, infinitely left, so as x approaches negative infinity of f of x is, again, 0. We're going to level out at that horizontal asymptote. Now notice, I had a vertical asymptote here at x equals 2. Look at what my x values approached at both ends of that asymptote. X approached 2 from the right, x approached 2 from the left, and one end went up to positive infinity, one end went down to negative infinity. So a vertical asymptote is going to be defined where x approaches that value from both the left and the right, and the y values approach infinity. Now, at the horizontal asymptote, y equals 0, look at what my f of x, or y values, approach. 0. Same thing here. So all the way out to the left, the y values are approaching 0, and all the way out to the right, the y values are approaching 0, which by definition then makes this a horizontal asymptote, which gets closer and closer and closer to a specific y value. The now try problem for example 1 is number 1. Find the domain of the function f. Use limits to describe the behavior of f at values of x not in its domain. So let's first identify the domain. that's going to be negative infinity to negative 3, and then negative 3 to infinity. I'm not going to graph this one on my calculator because I know very well what it looks like. That is the basic function 1 over x, or reciprocal function, that's moved left 3. So it's going to have its vertical asymptote at negative 3, but it's still going to level off at the x-axis. And it's going to have the same shape as the reciprocal function. So now I can use limits to describe the behavior of f at these values, not in the domain. So at specifically negative 3. So this end behavior up top is the limit of f of x as x approaches. So x is approaching on the x-axis here, negative 3 from the right. So I have to put a little plus sign in the exponent. So negative 3 from the right. Our x values are going no farther left than negative 3. But as we get closer to negative 3, what are our f of x or y values doing? They're going up to positive infinity. So the limit of f of x as x approaches negative 3 from the right equals infinity. The other end behavior at that negative 3, the value not in the domain, is the limit of f of x as x approaches. Okay, so x values are coming in towards that asymptote, so negative 3, but this time from the left, so negative. As we come in towards negative 3 on the x-axis from the left, the y values are going all the way down to negative infinity. And again, not required from the problem, but let's talk about it anyway. The other two end behaviors that exist here are the limit of f of x as x approaches, let's see, on the x-axis here we're going out to infinity. The y values are going to level out at 0. And then the limit as x approaches, so on the x-axis this end is going out to negative infinity. So the limit of f of x as x approaches negative infinity, those y values, their limit is 0. They will never actually hit it, but that is the limit.